market. So who is driving this? Let's take another look at this market-wide application, right? The computing is still the problem is actually growing in 2 years, right? The doubling of the total revenue and communications with the advent of 4G becoming 5G and 6G, there's a great demand of chips in communication industry. And whole the consumer is looking shrinking, but it is actually shrinking with the higher revenue model. So that is also growing. So across the one what mentioned is automobile, right? So automobile industry you see, it has grown from something like $40 billion to right 130 billion. That is the projection for that. So you can see how automobile market, AGI, conveying, auto, self-driving, driving, all of these are contributing to the biggest growth in this market. So if you see the common thread between all these growth in markets is the data, right? So you are able to collect data, unprecedented way in from different kinds of industries and things. So how do you handle the data? The data is all captured at the edge these days, and it is sent to the cloud and being processed. So that is introducing lots of security issues and bandwidth issues, storage. So this cannot continue. The overall trend is going to become that the process of processing of the data is happening at the edge itself. So that is the way industry is moving towards. That will involve some of the latency and things like that. So lots of innovation is happening for the processing at the edge. So this is a big picture. 40,000 level look at the industry, which is driving the industry. So little bit closer on the circular growth drivers, right? So we all talked about the Moore's law, which is holding in the semiconductor industry for almost 50 years. So as you go into higher advanced process growth, the yield is reducing. At the same time, innovations are happening. You don't let the yield go down. I'll show you that like how interestingly innovations have helped to keep up. The challenges of lithography, regulation have limitations, and what we have, the future trend is going to be the chiplet integration. Okay, let's see. Many other new people are coming to help us out, and that is where the industry is moving. And we are handling the data and improve algorithms or software and design intelligence in the chips, mainly in the design software. Without the design software, none of the things is going to be possible. I will explain that in more details. So better softwares and tuning hardware is required. Okay. And I will look at the picture, I will look at the data and how data is driving the world today. AI has is playing a big role. But at the same time, we have IoT sensors are everywhere. So we are talking about sensors in every place we are looking at. Right now, to every field of life, we have sensors that is able to collect data. Right? The health data itself is a huge market, and we have automotive industry, which is for all the things we need. We are using learning, generative AI, like ChatGPT and DeepSeek. How did they impact it for few weeks back? So that is how much. So when we talk about creating great kinds of technology, a small company in China has achieved something which nobody else thought of. So that is going to be the pleasant surprise. The scientific part of this research, people getting involved is, I'm so happy, you are putting extra effort to this industry because we don't want to verify to happen, but it is possible, and that is how the industry has grown all along. Right? Okay. So if you look at the data itself, right, the size of the data, I'm talking in zettabytes. So it's like the more than the terabytes, right? That is the one scale, about the terabyte. So zettabytes is 150 to 200 zettabytes of data is what we are trying to do for 2025. Right? So that means chips which have higher processing capacity and logic chips with bigger CPUs and GPUs and the network chips for communication market, and that actually increases the wafer volume. Basically, number of silicon generated is increasing like crazy. The volume is so high in operational funding and things like that. So we are using tons and tons of silicon. That's a different topic by itself. We are how we can manage it. Same thing with the data processing, right? The data processing is consuming a lot of energy. That's a different topic too. But somebody gave me a nice perspective of looking at data, right? They gave an analogy of comparing handling the data to something in food industry. So I was told the data is like raw ingredients in a food industry. So that cannot directly consumed. It is there. It's there everywhere. And how you are going to take the data and process it and provide it in a very consumable way, you need a chef. So that means purpose are so important because that data otherwise is meaningless. It's there. Globally, the companies that we have consistent data, but most of them they don't even realize at least 10 years back they don't know how to make use of all of it and they know how to many new rules are being formed, how to do it, what is called private data, how do you call it a public data, and how do you process it. So really, and the processing itself is a big deal, right? So it's like a chef, the chips are going to provide the right way and then provide the next dish for the public to consume. So there's a lot of work to be done. And this is about capabilities today, right? What we are capable of creating chips today, because building the chips is a small world. So I think the M2 chip from Apple, right? 5 nanometer chip is already having 124 billion, pretty complex chip. So that will be put in a commercial world, which means they are able to do it in a profitable way and able to sell it. So that is the capability. You are talking about thousands of transistors from trillions of polygons. Similar thing with the AMD chip, right? There's 140 billion transistors are there. And NVIDIA GPU has 208. And this is like an AI engine machine learning algorithm company called Cerebras developed. That is like a 2.6 trillion transistors there. Naturally, memory chips are having a lot more transistors there, and the memory chip for Samsung is showing similarly like 2 trillion transistors, right? So all of them were, and there are bigger chips are there. I didn't mention here because we have memory you can really go much bigger, and this is the kind of numbers we are looking. So this is something so complex which humans have not developed ever. This is compared with creating, making of an aircraft which has like a 1 million parts. And we are talking about 200 billion onwards number of parts. And all of them are so critical to work together. And the only thing right away, otherwise this is a very challenging complex task which really error based. Right? Otherwise, so all of them can be handled with advanced nodes and the cost is really high. To to do that, but the complexity itself is a challenge for engineers, right? So engineers want challenges to run their life, otherwise, it is not interesting anymore. So for that way, it is really good. So we have to have the challenges to do that. So quantum variability are more and more critical, which we were thinking that integrity issues which can be ignored 10 years back cannot be ignored anymore because power integrity and rest of the interferences is going to make your chips not functioning at all, right? Given conditions. And it's not kind of a challenge, right? Anything will change in the chip will change. So we need timing our layouts and layout our timing analysis. So we should be aware of, we saw that all the basic chip development trends are going from design for test. Test for power. All of them should be, all the components should come in advance during the design stage itself, right? We cannot just create my own design which cannot be synthesized. These are the typical word 20 years back. Now, if you can create a layout which cannot be passed in timing. So that is the kind of, this is much bigger challenge for a much bigger project or the number of transistors we are running. So the results from foundries are also very demanding. So they have to provide the ingredients for the design company to make those chips, right? So the original thing comes from the foundry. So the basic technology files, we call it, I will explain more in the future slide. So basically, they have to work with effort for the design company to develop a specific process. And so they have spent a lot more money to get into that right there. On top of it, they develop and they provide infrastructure and they have worked on very high technology which are expensive. So I am on top of it, we am trained to work. So that is the reason, in the given advanced technology, it becomes a real high quality impact business these days, right? If you look at this number of foundries in the market, that shows we have 17 foundries in 2001 working on the top-notch advanced technology node of the day, right? 130 nanometers is pretty good. I remember working in 65 nanometers, and when it came down to 2016, like 16 nanometers, there are numerous challenges. At the time, I tell you, what are the challenges we face. This is very interesting to see, the cost is really given so high, anything on step out. Right now, Intel step out of foundry business as of last year. Right? So two fabs are able to do it at this time. And if you see, the TSMC's revenue by technology, the advanced nodes, 5 and 7 nanometer, is almost 50% of the revenue. Even though the volume is less, but they are so expensive to use in that particular volume, the technology. And they will get better as we spoke about. As the technology is developed, the cost will go down, but at the same time, the system our number of chip makers using the older technology are also less, right? For a good reason. Because the number of transistors much less energy input. So, even under perspective of the cost, right? There is inflation when taken into account the cost. Otherwise, from 2006 to 2020, the business and the real advanced technology node is costing 18 times. So this, the number of, however we call it, design of chips, design of the highest load, the high intensity, the high density of transistors coming in a specific area will not justify this kind of expense for that matter, right? So if this has to be handled, we need to handle Moore's law, right? So really, before the year 2000, right? This Moore's law has been like 1971 is there, right? Every 2 years, transistors is counting doubles and then follows better performance. That's what we thought, and we were just happy scaling area until late 90s, right? We thought this is going to continue forever, and technology nodes, we are going into from 130 nanometers, 65 nanometers, 45 nanometers. It will 22 nanometers, look very good. Then came in the year 2005, we started seeing some problem. Actually, really became a challenge. And starting from 19 nanometers, going by this graph from IMEC, right? Then it was very difficult because people knew that when you are going to touch 1 nanometer, we are talking atomic level. So there is no way you can penetrate a transistor at that level unless you have to invent something new, right? Then it went on, kept going at 20 nanometers. I remember the industry being double patterning cost, right? So you cannot just design a chip and then take it to the physical verification with single mask layer. You need to have double atom, otherwise the impact will not be used out. When you have to do 2 masks, it was double the cost. So that is where the bigger challenge was. Around 16 nanometer, I would say, the graph is 14. I worked on 16 nanometers, and at the time, that is one of the best times in the industry, I would say, where FinFETs, new way of transistors were invented, right? So transistors are considered the MOSFETs we studied they're all planar devices, flat devices, so easy to fabricate. And there was a talk about using FinFET, FinFET devices which are 3D devices. But how you can fabricate, and all of them were a very good question, and totally it was ignored by the community in the beginning. And at that time, when the costs were too high, somebody tried to put it into work and created the characterization for it, and that delivered. So with the advent of FinFET, 16 nanometer onwards, we were able to maintain the Moore's law. So because density increasing very well, and FinFET has its own challenges. It had a own model of gate instead of planar, which is very easy to handle. And nobody could imagine the linkage currents, the single integrity is caused by FinFET. But it was handled so well by the industry, and we are continuing to scale further, and by 2015-2017 we were able to double the number of transistors right? Then came this DCP and the STP I will talk in the next slide. Right? Then at around 5 nanometers, right, another big invention came. So this double patterning lithography issue was solved out by one of the European companies. They came up with extreme UV invention. Imagine how these inventions keep coming, because there's a necessity for creating power chips, and either it happens at the design stage or at different methodologies or different equipments which make the chips. It keeps continuing to happen. So you can see that in multiple decades how that is maintaining. So we have to see that how this particular Moore's law was mentioned was amazing to think about it today. Then it reduced the cost of 5 nanometers. Otherwise, people would have dropped out of 5 nanometers and thought about creating other variations like the chiplets, which is happening today. Then different levels of scaling, right? So the hybrid scaling and new paradigms like quantum is also showing up nowadays, right? I will show you a simple graph with another way of looking at the same thing, right? So here we are talking about device architectures help until 16 nanometers to maintain and keep the cost and make it profitable. And so design technology go up after innovation started happening. The DTCOs and the system technologies also happened. So if you talk about 7 nanometer yield cost reduction, then what is then we are coming with newer and newer devices, like the scaled FinFETs. So FinFET scales are not the fins are not one anymore. We are trying to make three and making it vertical, and this is gates all around in the next wave. We are trying to create new devices. So these are all the innovations that happen in the fab side, right? So create them. And with this scaling, most likely valid. And then if you penetrate the content, you will not have a problem. And by then you will have some other innovations. So that is the speed at this industry is moving. So if you are, little bit slower and hope for 5 years, you are going to work on next generation technology. So that is the thing you should be aware of. So coming back to what is driving? So who is behind all these things, right? So when you invent, for example, printer technology, there is a lot of software tools, right? We have talked about that is needed to design these, impossible transistors, the impossible chips. So we have to make sure these manufacturing requirements are met in the design system. And someone mentioned, right, one of the CEOs of media industry mentioned, without my company software, not a single complex chip can be manufactured. That's a very big statement in this industry, right? So you will think that every there is enough people in the competition to do it, but when one of the engineers can say that, that's actually true. So there is, you can make with many other software, many other tools. Without it, we can create a chip. But without a specific group of software, you cannot even make a chip. But the irony is that is not the biggest profitable business in the market. They are only software providers people are making the open access. So that is the fate of the industry. Right, so medium is there. Without electronic automation, there is no chips possible. And basically, it's about simulation. Right, so we have to design. You have to verify. Verification takes more time. There is simulation and physical verification, and there is hardware emulation and prototyping, and the semiconductor IP. This is not the standard definition for IPs. I will talk a little bit more on this. This is mostly reuse of designs, right? And so these kind of terms, right? Analysis of simulation and static timing to make sure the chip is passing the manufacturing test and the design rule checks. This parasitic, right? The layout impact and the synthesis, right? So we also have high level synthesis this time. So our design doesn't start from RTL Verilog code anymore. It starts one level above the architectural level. That is a trend that has to go forward. And floor planning, logic synthesis, placement modeling, all of that. Yeah, talk a little bit more on the EDA is the value add, right? So when you are talking about billions of elements in a system, and each one of them is modifiable. So once you modify, it can impact anything, and functionality has to be ensured with tons of additional logic, and making sure that the area we use is a very competitive level. You cannot just create make our design work and create a huge chip out there. It won't make sense. Basically, you will be not competitive to be in the market, right? So the automation has to become really sophisticated because cheap errors, right? They cannot be patched. Once it is done and if you want to redesign, it is too much expensive. Basically, that company has to wind up. So that is the risk that is involved. So that shows the importance of this software tools involved. So just a touch on what the market segments are, right? So this is design software which it started for simulation and we call it front end and back end flows, and then the PCB design flow that everyone understands. Then we started creating IPs. So basically, just like the standard cells are repeated across the chip to reuse. So these companies started creating my verified way of giving a design which you can reuse in your own bigger designs. So that kind of library for CPUs, memory, IPs are available. That actually has grown tremendously, in a couple of decades. It has become almost like 10x of the revenue. And then naturally, service business is there in the markets because they have technology, they have the know-how, they work with the foundries so closely, they need the services from them, this industry market segment. Right. So where is opportunity coming? Because AI is really driving the world, and all these the tools are also designed with the help of AI this year. And security is a big concern. And now we talked about importing chips, right? So why a specific country is banned from importing? Because people are not sure what can be part of the chip. So the chips can have this is all working on wire, and the whole future warfare will be can be through. That is the fear people have. So we want to have everything indigenous, locally made, and it's not just because the money and the challenge are there, it's also security. That can cause further attacks and make your banking system go blind and go blind. These kind of things we have to expect in the future and get prepared. So new technologies have really grown far, it's been their own increase. All of them are expecting better software to develop. 3D design survey, stack chips, it has challenges of making them work. For that, yeah, because as I talked earlier, right? So about where do you want to process the data? You want to process it with the edges, so that wherever you capture is processable. So you want that's where it is captured, that's where it belongs. So your personal health data, for example, you don't want it to be sent to the cloud. Even any country's laws, they say that we have to keep it within our own system. So for that to happen, your sensors have to be more, which they have its own processing power that will increase the cost. So that is increasing the rest of ICs in future. So this kind of things are coming. Like the same thing applies to military, right? So the chips are in security and in defense areas. We are putting, so we cannot afford to have a chip imported from a not friendly country to put into our defense, critical defense missions. That's a very big challenge. So taking a quick look at the ecosystem itself, right? So I will start with the top, the bottom left corner. So that's where I belong, and that is the most interesting part of this particular whole chart. That the EDA tools. So even though they play a small role, they play the most important role. Cadence, Siemens, Synopsys, and Keysight, and Xilinx, and for FPGA control. Then IPs are coming from ARM and the rest of them. And then in terms of copper semiconductors, which are so it's low, but too many of them. The capital equipment like ASML is the one who invented the machine that changed the world. And material, constantly materials get invented, right? So silicon alternatives are being investigated and staged upon for the past 20, 30 years. I was part of some research in the T5 periodic table levels, gas and GaN. They are all realistic today, and we have chips based on gallium nitride, which is actually the main industry today. So similar, IDMs, so there many of them wanted to go all the way, design and then fabricate themselves. Even though they are shrinking. And coming back to this side, bottom row foundries, right? So there are only two foundries of the technology node. And then this assembly, many of the chip assembly companies are there, and PCB makers, sensors, EMS, OEMs, and the cloud software, right? Who thought cloud software would play such a big role? Right? Basically, amazing, right? Amazing. You want today to do all your EDA simulations, you have to be on the cloud. Otherwise, you will not afford. And this kind of things are coming from healthcare and providers, right? So, I'm interested more on this. Right, so with like a trillion transistors out there, there is no way we can predict the changes, right? So power performance area cannot be met. The goals will be very difficult to meet with advanced nodes because we are finding more and more challenges during the linear way. That's all these flows we talk about. Okay, those days you have the right to design in RTL and take it to synthesis, and then from synthesis you can take it to placement. So those are not easily possible anymore. So this whole flow has to go from linear way, handing over inputs to outputs very easy going with all people. Now it is becoming concurrent. So the concurrency we saw it at mixed signal level when I was working on some of this methodology development. Right, you cannot just think about bringing the digital and analog world together. You have to think about it much early. That what, how they interact and what voltage is being designed and things like that. So, so these what-if scenarios are really driving, and it is making big challenge for the possible variations. And so the verification is taking 70% of the design time. So basically, the design itself can be just written. The designers are so rare. They have to think about whatever has to be implemented in a design way and write the code. But that time is, if they don't write it in the right way, it cannot be fabricated anyways. So the verification is playing a much bigger role across the whole this ecosystem. So someone talked about these softwares are costing billions of dollars. And I was laughing. Yeah. You have to see what if you don't spend that money. So you don't charge, I'm not spending money on you. Obviously not. So they are expensive for good reasons because it's very comfortable already. We used to sell in Cadence, right? So if at all we made a business model with the chip companies when Cadence was formed like 70s, 80s time frame, that we don't license the software based on the licensing. We just want 1 cent or 1% of your chip revenue. TDA industry will be as big as NVIDIA today. That was a very big mistake because we create two competitive markets to shoot each other's foot. I have no better word to say. So that is how there is a design. So this is such a critical thing. So we must have patterns and initiatives happen in this area. But even though I would say that they are not relevant enough. So, being part of the industry is very difficult to say because for you it's concerned, but that is a fact. Right? So, it is, considering your design will fail in the future, doing the simulation thoroughly or spending more time with software tools should not even be a question out there. That will make it on this. Right? And how do you make all this software work together? We are talking about the 300 different software. I mean, there is no single person or single technology engineer who can be aware of running through this software from system to fab design. So you have to explore in every single area. Like take almost some like take what the categories of software out there to design the chips. Right? So everything you want to create system level design and create it. That is a separate suite of software that has been developed and maintained. So CAD is so important. And I would say, so you want to put emphasis on CAD flows. Usually the members will provide a reasonable amount of flow themselves, but there should be local expert in putting those tools together because what I hear, right? So this software, we test on this software and run the simulation after there is 5 simulations run for sometimes 5 days to couple of weeks it can take based on what you are trying to do, right? So it comes back to me after 5 days and gives me a syntax error in one of the input files, right? So that is the kind of challenge we face, and imagine the productivity is not out there. So you have to consider that and also the support for these tools. So make sure that this tool is very important. So this also is a flow which touched by multiple people. I'm trying to give a story of where these things fit together, right? So it's a general digital flow, I would say, and so we think about the whole product definition and put that in Orbian or System C code and make sure that that is synthesizable. That has to come into gate. So that has to be synthesized to make the logic gates. So that is the challenge when you write an Orbian code. And you verify it with Boolean simulation, which is plentifully available, and change the cloud code and all your DLP and the rest of the logics for testing everything added to that. Then you bring it into layout, and then you open the layout, create your masks, and test the wafers. This is the ATE. The previous session we talked about the automatic testing equipment, which is like a $5 to $10 million equipment. We need to test that. I was fortunate to work on this at a point of time. This should be done in a clean room because there should be no dust. Even this is testing manufacturability. So that has to not even minute level dust can show that you have to be property. So it has to be safe. But there's all very established tools available today, and packing and system integration. Right? Keep going. So similar flow for custom your digital design is so common. Anybody can put the idea together and then bring up another chip and completely. So people do a custom design which for their own specific industry. They make their own choices for design so that they stand out from the rest of the crowd. So that's why where you start with your schematic, you will end up in the field and the bottom flow remains the same. So, okay. Yeah. So talking about academic procedure, I thought this is more interesting for you guys to see that how this has never happened. This is actually a golden time of semiconductor industry, I would say, where industry, fab is coming, 100 design process is given to the education industry, and we can generate our own designs and get it fabricated. This such an opportunity is not available until this point, and Kevin has put together the education team to increase bringing colleges and universities into this program. That very clearly says the scarcity in this market. So, number of people with this particular design now is lacking. That is what is forcing these companies to come with such a program. So, you can even get this process design case I will explain in the slide. So, that given by this particular foundry in Europe is actually helping us, the education institutions to get into this game. This is very interesting. They have no, here in GPT they are doing. Those are not fabricatable. They are only you can play with. That is their server. That's why this is different. They are there for 20 years. So this one is introduced in 2023 or 24, couple of years back. This Sky 130 is a major breakthrough in the industry. I am not talking about the GPT case. GPT case are available forever. That's a general thing you can do nothing with it. Right now I am dealing with company I cannot mention here, but there will be a company with dealing with this process, and my software will enjoy it. It's not, they can do it, but it's a little not the top technology design, but you can, the idea of the education institution is important because we can make sure that one such a flow can be put together with where we talk about this software, this one, and all of them are coming hand in hand. So that is the takeaway in this slide. There is no idea. I'm not guiding, but something to investigate. Definitely interesting for this particular group. We have the restriction only to deliver with the GPDK. Once this is available for the teaching and it is. It is. That's what I mean. That's exactly what I mean. That's why I didn't even bring it here. So we need to see. I'm not done with the restriction. That would be a it is there, and I would kindly assign that to this community. I hope it is. But there is something definitely worth investigating in this area. It is there. It is not like GPT or anything. GPT is just for making the software that will always, because somebody tested it, it will not show the real problems. So this is the kind of challenges we face, right? It needs system knowledge, software knowledge, design knowledge, what the design is trying to do, what SLD put through. It is very complex. The debug sections in chip design is very challenging if you want to talk about it, right? So here they have put these are two which are available in the open market without any cost. Some of the these are digital flow with the kind of nothing to do with the government personalities. You can see these are available tools. So for universities is more interesting, and the same similar flow for analog custom design flow I talked about. And I also captured all of these. So another custom design flow, and I provided a link here. You can search through this semi-VP. They have provided a list of 50-60 tools, which to bring into real commercial using a open access tool. I won't recommend because there are lots of challenges. Time is money. Plus design time is not for free. So when you are putting hundreds of designers' time and effort using paid software is definitely worth it. But training and rest of the model, but this is the way industry is going to one open access flow for designing chips. But it all depends on how much of time effort we can invest there, and then let you know for a while the price is then the cost you are paying. So there is a challenge out there, but that remains to be seen. Okay, so this is my favorite area. So we've been working on this for decades. So we like to spend a little bit of time on this. Right? So when you talk about speed and accuracy cannot come together, right? So when there is speed, there will be less accuracy, and when you test your accurate, you will take whatever. So where do you draw the line, right? But chip has to be simulated and sent to the market. Time to market is the first time, but we have got RTL design. So I come from the bottom right bottom area, right? When you're running pure digital, your design with your system C or system Verilog model, you can put it this bench, make sure your original requirements are met, and you can simulate it so fast and then say, wow, it all worked very well, right? So that can be 100 times faster than the real spice. After you go through your other steps, and you say, I'm coming to the top left portion of this slide, right? This, when you talk about spice simulation, this will take like 2 months of time for your application. All the files you put together, and then how do you do it? That will take 2 months of time. So we have to have a balance between. That's when we invented. I was part of fast balance tool when it was acquired by Cadence, like a couple of decades back, new software, and that was becoming famous these days because they were trying that you have. See, spice is nothing but solving matrices, right? So all the math base go into there, and then they just look at it as a mathematical model and algorithms. So given all these parameters, they look at this matrix. How can I solve this matrix? So there are 3 zeros here and there, 2 zeros here. I can take out these columns and these rows out. When you take out those along with the rest of the elements, this is something accurate. So if you don't want to do everything, it is like in life, you don't want everything. You want to give up something. So you don't want to give up everything you want to do. So that is the balance you have to make. So that worked actually very well with this quantized tools came to look at the market. They were able to do smaller, very complex design. We can best do a spice. Spice is the idea, right? Once you have a spice for the whole chip, you can be very sure that this will pass your manufacturing test. But only challenge is impossible with the fluid and transistors, right? So then the content works well. Then at Cadence and the industry introduced online models, like Verilog GA models. This model is analog based, but it is written in hardware language, HDL kind of language. So when these models are introduced, Verilog AMS, we put out the information over there. You can say, some of these blocks you can take out your Verilog model and plug in spice models. Only for your PLL block, for example, we talked about that design, right? So PLL has to be part of, even if you find a full design, there has to be PLL, which is analog, and that has to be integrated with your rest of the designs. So, but how do you verify that is working well? Yeah.
I have seen both way of designing PLL, like full custom and this chemical custom. So which one is the better method to design the PLL?
Designing PLL itself is a complete challenge, right? So I am talking about doing a PLL block with PLL. So if it's block design, it depends on
This GPU is a separate unit of PLL. GPU can be designed by full custom, and that can also be designed by Verilog. Like big detector, that can be designed by Verilog. That block, the separate block can be full custom or can also be semi-custom. Method is more.
Analog is much better. Absolutely, but how you are able to go to design because of two categories. There is a model, there is a model available, which is capturing most of the density, but there could be missing points. but we can afford to some extent. So if we are mature, we can talk over there. So there is another way which is going, which is actually going very well. And at some point, I'm still surprised that the percentage, the design I made to work analog and digital separately, and then they say that no, it's working for us. Right? They take a chance of getting it done. So it's still there. So real number modeling really got into the market. So now many of these particular models we can use real numbers. Numbers can be simulated very fast. So it is as fast as one, but the challenge with this model is you need to have experience to write them. So how do you verify the model? Actually, there is a tool given which compares the model. It's interesting. Everyone requires, right? So there is a big necessity into DevOps. So, but you can actually compare with the spice and verify and virtual all these things. Then it's a big question out there. So basically, the career is to do so electrical awareness in system management. Right? The two people know does not know about analog aspects. So we have actually language is mature to that level that we can say that EENet current we can define SDL in system level. That is the EENet. So those models will be very closer to that's what is making real possible actually. EENet I have here, right? System log EENet. And the model number modeling. That's normally very famous in the EEN and very long. Right? So let me talk to some of the flows, right? This is from for the communication industry. Pathway EEN provides a corpus for designing product design. It is because right, we can talk about the most of the design is done in open access, which is cadence scale, open access models, and make it available to rest of the company. So they are able to build the open access those layers and provide additional features and the leaders in the methodology design all designs. Right? They have their own solution, which is loved by the markets out there. So they import layouts, they begin the IT is a native RF design. It is just for RF designs, and then later we are verifying these layouts and bring it out. So that's one flow. I hope you are going to cover. So this one, you see, this is the cadence ADE. This is from Golden Gate solver. Right? The RF spice solver is from CSIT. But even cadence their office they allow solvers are pluggable. So you don't have to use the cadence solver. You can generate the layers because spice is at least 50 different varieties of spice out there in the market. Even though it's different thing, sometimes you wanted to look at the costs of running spice machines or some other advantage we have. So Golden Gate prefer they use different bit of cadence. So that is possible. And because it is definitely for out of design it is preferred. Yeah, let's talk about I am doing typical methodology how the industry is going towards. So you have to know you have a connect between the how it started out of this and how you can arrive at. Right? So here, so this is market leader, right? So even though some of these audience videos, so with our own force, there are market leaders, right? So this we need to do without smart system. Right? We had such a big challenge at one point in time, and the cadence was limited to the SDL itself. Right? So yeah, that is the original invention, and afterwards Kubernetes came in, and the cadence is really the analog world. So now when you say I'm using cadence, it is a very good invention also. That is the kind of norm. I go to this kind of they name the body with another. It is not with parents. So there are not exposed tools out there like that. The human were before before, and they have been to they are doing this video world for almost 50 years, and there is nobody can go close in this application. They have saturated in this market, so they do this best, and Canada is de facto rule if you want to do a chip work with the fabrication. Right, so how what kind of things they do? There is like multi-patterning and pattern matching to make it faster, because now you have 2 trillion polygons of black and one file with PDK. So they have also new flows. How we are reading number of steps that is needed for the layout versus schematic. Right, when you create a layout, you need to functionally correct with whatever I designed in schematic. Right, that is the next challenge we have. So they are introducing construct by correction flow. We call really evolving every couple of years. So let's take an example of a typical SOC, right? So we talk about a typical chip on the system level with the system on chip will look like this. The CPUs and the RAM and the digital cores, and the bottom row shows the behind IPs like PLLs and the IPs. How will you integrate them together? So some information in the process design kits, this is required to be, this is the one I talked, if you recall, the beginning of this case I talked about, fabs are putting a lot of effort to create their own infrastructure that has to be shared with the designers. Like they provide for the backend solution, they provide PDKs, right? So the PDKs is specific for a specific design. For example, if you say 5 nanometer, you need to use 5 nanometer PDK to give up a layout. So it will give you the violations to make sure that it works in 5 nanometer design. How do they do that? Because they try trial and error method on some small designs and run spice simulation. So they will be running spice all the time, all the boundaries. And based on that, they characterize a model. So Verilog and rest of the models they give. And that model is used for standard cells and DRC root checks, all these simulation files. So doing library and simulation models, they are all provided. Based on this, when you simulate, we create the layout and then do first layer simulation. That will be much closer to what foundry aspects. So this will very type of road is the flow. Where you used to be seen from the bottom, right? Which was Spectre, spice simulation, and caliber, Pegasus, DRC checks. And all this plays a big role because this PDK is made by every step of the methodology and ensure that the impact is met. So it has to be done from the beginning of the flow, so that will chips are probably that. Right from the call it EMIR flow. Right, so when we talk about that, I mentioned EMIR, here it comes. So power integrity, right? So we used to have tools which will estimate the power of a chip, right, based on the RTL. And I remember the specific company was bought by Intel like long back, but many of the companies disappeared because I personally was involved in measuring a 3G chips power coming out on like 40 watts of power. They did not go to so that's what happened. So power is very important. After we remove it all, So this is a comprehensive system level sign-off, right? This sign-off we talked about. So the Allegro is the PCB level challenges. So after you put in the chips on the PCB, system level verification is there, size, flow, and you measure electron migration and ion drop. Right? So these are the manufacturing defects that can come in. So that has to be simulated very in advance in the design, and ion drop has to be found very in advance. So for a full chip flow, right? So Fluence provides such a nice integration. This is a concurrent methodology, right? So those, if you take 5 years, 10 years back, you just decide on your intervals some different people. So on digital integration platform, you don't want to worry about signal integrity or the power IR drops. So custom design will come in separately, and unknown design will hand off to the design teams, and basically digital will work totally isolated, and both of them will be fine. Because we have created the power, and if it's we extend the sign off, we make it bigger and more power consuming chips, and we are able to serve it. But when it is demanding more and more, we cannot continue to do that. So we rely with that open access, which was developed for the analog design. The database is shared with the digital design right now. As you create your layouts, it will be momentaneously by the digital implementation folks. And I was trying to say one thing, the electrical aware. So how is water changes in the design, how electrical we are aware is also calculated, and those flows come together on a utility platform to deliver PGV, they call it, right? They call it, that's a grid. They show the power grid. Yeah, power grid view, right? So you create a power grid view to show that this kind of spots, right, where these ion drops are high, and what of range that can be done so that you chip will pass through the power grid features. So this, we are talking about the full chip running with ion drops will involve lots of SPICE simulation and lot of verification checks. And these we're talking about 16 core or 10 core machines we want. The most important features you have to throw in all of that to make some simulation like this. That will take 2 months in typical complex chips. So that is the kind of effort that is involved here. And so let me go fast. I'm running out of time. Integration. So yeah. Okay. This is what I'm talking about. So we are solving. So the quantum is the common solver they put together. The extraction is you are extracting all the parasitics from your layer, and you put all these digital and analog flows together and share the common database, which makes it straightforward to read. There is no handshake anymore. You cannot do it linearly. You cannot afford to go linearly. That's what this flows do. Right? This also shows how it is working on the cloud. Same thing with the power sign-off. Right? When you want to do the power estimation, so you have a spec on which you have worked on. I am going to develop. Somebody gave an example of have your medical device you are creating. So medical device power is so important. Right? So you have a battery and draining fast, so that it has to be really low power. And if that low power intent is put in the beginning, right from the high level synthesis, you need tools to make sure that you are right thing. Because the design can be written in 100 different ways and still make it work. So how do you make it in that one specific way, which is not take power, will not have a testability challenge, will not have, that is where the designers have to measure into. So that's if the tools will force them to bring that specific design. So builder AI is playing a big role because all of these opportunities which humanly can build out all of them are captured by these AI tools these days, and that is the preview of my forward slides. So, but the idea is you want to have this power awareness built into the design, right from the beginning, into the digital implementation, place and route, right from the beginning to final to final. All the way you take the power and feedback, and then run our conformal and checks, and then you create this ADPs, what we talk about, the patterns for testing. Right? These patterns will go to ATE for testing after the silicon is created. So there comes the idea of creating these tools with LLMs. So these are the new concepts which machine learning brought in to the software world, and that the software is just being brought into the EDA. So the tool which you have to parents 10 years back, if you use it, you now don't have any of these capabilities, and they are basically worthless. So this is the kind of inventions they keep bringing in. So this LLM model, this is bringing the layout effects into the picture and allowing our timing analysis. Okay. So this is not LLM slide on the slide. Yeah, this is for physical automation. So how the layout is going to have layout success depends on the neighbor layout. So you are definitely checking the neighbor. That is what these checks do. Right? Yeah. Then is the design game. This is the local layout effects, right? So exactly. So the airport can change the neighbor pattern. The neighbor pattern has to be moved in the layout itself so that this will pass. So these are the things you can predict. So this is where normal design humanly not possible to do certain things, which these tools are giving an advanced prediction. Exactly.
All of these type of tools like the BIMLs are available, or whether this is not essential job of.
No. These are only helping us to. Otherwise, we cannot even achieve this 2 million goal. So how do you say, okay, AI is not going to take away human job? Okay, my personal perspective on this very important because AI is going to be as is trained. Okay, you can train AI in wrong way, you can use wrong results. That's to be validated, but that's how it's going to work. So anybody can create models are going to just follow. If you are given wrong inputs, you are going to get wrong outputs. So it is not going to impact anything at all. It's only going to help make sure that layout is, otherwise it cannot even be done. This will be open end forever. You will be sitting on it forever and the chip can never be taken out. So that is the challenge this is solving at this point, at least. Right. So yeah, this is the whole reusing of the IP. IP is intellectual property. Everything in the design is IP, but here it is more of reusing the existing DSP processors and everything. Here, an example is I'm putting a same design is only the green part. The rest of them are just outsourced or bought out. You can create a very complex chip with this kind of things put together. So very quickly. So this is where we talk about these concepts. That is the reason I think industry has market has grown pretty big for the CDA industry. Right here, I come with JRE program. Right. So these AI enhanced tools, right? This is only helping. So how this formal verification, right? You could have checking from RTI to gate level. You converted all the code to gate, and how do you match it into matching each other, right? Here, I have time, right? Another 10 minutes? 5 minutes. So, could I check? So, AI enhanced tools across the whole of, education, Monte Carlo, regression, FTA, and library characterization. Once you characterize with AI, that is going to be into with rest of the building blocks, right? So here, as you see, all there is a AI cockpit is here at the center, doing some debug and semantic dips and stuff, but all the tools are already separated flows in the cables, right? So Jasper performance application, digital simulation engine, Xilium, Palladium, that emulation hardware with the prototyping protein and virtual platform unit with the Helium. All of them are working independently, all of them are working different guidance from the Delivery platform. So this one has to be. On this, I will have to spend some time on the domain repository, right? So yes, take a note of this. You will not have seen this very often in the project flows. I will, that is my favorite topic. I will touch on that. Okay. So again, this one is actually having lot more impact on the architecture to how the technology is built into different flows. Right, what is to be touched here is like if you are working on the cloud, this is working at the architecture, this is how the yeah, so basically it improves the productivity of the whole flow, right? So additional inputs will be given. We know the methodology is developing in the future. Right? Implementation is the optimization of the flow becomes much easier in this kind of platforms. So this I'm just touching back on the manufacturing process quickly. So we talked about the lithography process, right? Once you have a medium ready, a photoresist is applied on the wafer, and that impact on light till the same level, and that creates the epitaxial growth, right? So that's what one layer of metal is created, and the rest of them are it's out. This one is pattern technology. We talked about EUV, all of them are still important. And this takes 2 to 5 years until you create any of these days. I think at least 13 metal layers are there for the design, complex design. So that is done, just for knowledge. And this is my favorite topic. What is design data management doing in the IT industry? Okay, this is something very critical, and mostly DIP does most of the work for the digital world. But when it comes to analog world, you need to have a real-time control to manage the design data, and you need to have which versions of because your teams are going to be in different geographies. They are not going to be staying together, and the old ways of bringing all this, hey, my layout is ready, I will send you by email, download this email content, and then try your step of the layout. That is not going to work anymore. That is gone long back, and we are talking about one team will have data in small projects. So, and if you want to protect your data, your designs are very important. And if you want to have some contractors working on some portions of layout, things like that, and you don't want to expose your, and there were some security questions. So you don't want to expose the whole of your design to everybody. So you wanted to give portions of them. You can make it actually. You can make only one particular layout visible to the contractor. Rest of the designs will not be visible. And within your design and layout teams, you can say, a layout team is just doing the layout, and design team, they cannot even use the schematic. Things like that, we wanted to have control. It's a very customizable control, and they also be used all the chip, because you want to use one chip for the next generation chip. Most of them are going to come back. So you don't want to have the extra modifications there. and the data. We wanted to do very fast. This cheaper as much as we say the demand is lot more. When you are doing SSDs or chip design, it really adds up to the cost. You don't want to think in your say 50 GB of layout created for 10 different designs lying in your disk. That will consume a lot of energy and also space, and it is so difficult to manage. How that can be handled with a top level set of software, which is not as especially as rest of the design tools, but this is an integral part of that flow. Right, so bring that up. So another tool, this is engineering life cycle management. Right, so PLM to be heard of in the software world, they are very complex. It takes like 6 months to put them in place for big industry. But even not that big for IT. So we will only add lightweight PLM. This is engineering life cycle management. But you do have a lot of IPs from different places, and you just open access software display is working. You bring in download from internet and open your chip. However, if there's a loss out there, what are the IPs you are using the chip? We should be able to tell. These are the things typical designers forget to think about. That's close to the whole company. Right? So that's critical. So we need to have a way to find out what I am using as needed for my teams. So that has to be listed out very properly. We use some smallest level of tools. So before using an IP, make sure that your engineering department approves it, your marketing department approves that this can be used within our design. So that kind of things are needed.
A lot of their concepts have been brought to the tool.
Very nicely brought in. These are like concepts which you cannot. I don't have time to discuss about it. 1 full hour on this topic, which I typically give to industry. Yeah, software tool, and also what you are using to design.
Incremental license.
Not the license only. No, even if you are using some PLM from a specific company, that which version of PLM you are using. They might have given you 4 different versions, and then I have removed this specific security concept in this. Use this version, and make sure that you use only the specific copy into your design. Yeah, that has to be saved as a 2 different way copies in your system somewhere. Yeah. This is a tool which works. This is a TIFO tool, and which I work very closely with this team. So this is okay. So the company I work for, Creosoft, has been acquired by Keysight, and these are the tools we brought in. So I am much closer to how this things are traceable. So this BOM is important, and that should be traceable. If you are not using those BOMs and finding out what is used where in your design, it is very big cost in future. So for that, you cannot bring in a PLM into your flow also. That will be too expensive and too time consuming. So we need a lightweight PLM. This is nice thing to really try out for the industry. It is GitHub. GitHub with a lot more than what GitHub can do. So GitHub cannot do anything in analog world. So I will show you. That's why I have no time on this. So this data management is tightly integrated with the analog designers. So they are talking about design hierarchy, which GitHub doesn't understand. And Git is taking a lot more space consumption. These tools can bring in different technology. There is a lot of technology constantly being developed. And we bring in only links. You bring in 1 copy of the design and then link to 50 different users, which is saving you tons of space, security, things like that. That's a different topic by itself. Right? That's
giving flexibility to the students so that they can have their IP.
Yeah, of course, you can say your own, but this is like like physical verification or front-end flow and like synthesis. This is a separate topic of discussion, and it involves that kind of software and knowledge. Right. So now new concept of quantum is coming in everywhere. Quantum computing is getting everywhere these days with chips, and that is after the announcement of Google on Willow, right? So there is amazing world changing announcement, right? So until then, people do not have confidence on quantum. Now Google is showing that it will be so accurate and whatever we could not imagine all these days is going to be realistic very soon, right? So that is the kind of impact this quantum computing has, right? So when they are saying like 16 qubits, when the number of qubits, quantum is accurate. So nobody could afford that kind of high investment all these days to find that particular fact, which Google did, which is really amazing. It's going to change the world in a couple of next decade for sure. So we have some software tools to do how the qubits quantum technology can be used. So this, the last but not the least, world-changing technology in the design software is coming into chiplets. So the whole idea of doing microarchitecture, execution, logic gates, all of them are related to physics, right? So the atom level is what is driving the industry. They are all coming into chiplets. This is going to be the way the next level of methodology is going to work. And here, to continue praising the Moore's law, it is going to continue for another this decade at least. We have more dimensions than in the packaging industry, right? How you can put multiple die instead of the old method of multiple chiplets there. It's brand new concept to intervene, and how you can put multiple chiplets on a single substrate. This is going to change the world. And to make this work, existing tools are not going to be sufficient at all. So we need a brand new tool set of new tools. So as you say, we need some kind of way of helping hand for us to achieve all this. Otherwise, we will get stuck. We know this is the way to go, but we will be stuck with not, just having knowledge is not enough sometimes, right? We need that as a helping hand, which is bigger than that. Is why we have computing power. So that power will be needed here. So that's how Cadence puts the future of design automation in a single source conflict. This is really amazing, and this is as of 2025. Right? This is I'm waiting to see what kind of tool they do, how it is going to be. We all learned about the application. When you look at things coming, that is what is carrying on one side, other part is that's what is good for you. Similar way, I am putting overflow from Keysight and chiplet technology together. How data management, changing of your cataloging your IPs, finding and comparing which IPs are going to be used into the engineering lifecycle model and publishing to the chiplet, and then use an integrated solution to these chiplets together and the chips are stacked. And also chiplet. This is the kind of things used to really another mention of reusing of the IPs and the materials. Traceability is critical. All of that coming into the picture. So for taking a little bit more time, hope you enjoyed it. Any questions?
Energy density is the important term also because we are talking about the power consumption.
That's why power aware tools. When we talk about power
EC department, basic safety Bangalore, to honor the speaker. Noida. We will have a tea break now. I request all of you to assemble back at 4:15.